So you're all warmly welcome to this virtual workshop in high-performance computing for wind energy. My name is Atanas Popov and I'm Professor of Engineering Dynamics at the University of Nottingham in the UK. Since May, I have been also the project coordinator for the HPCWE project, and this collaboration between partners from Brazil and Europe. So if you allow me to say a few introductory words as a kickoff to this workshop. The current workshop is our second annual event. We ran one workshop in the middle of September last year. The aim here again is to present to a wider audience and to make available to other researchers our latest research and development results on the project. We are also pleased and at the same time honored to have on the workshop program two eminent guest speakers to present their research findings. In terms of the scope of this workshop, the worldwide demand for renewable energy with significant power generated by wind is a well-known fact. And people who work in the wind energy sector are fully aware of the challenges in the adoption of wind energy. The HPCWE project aims to address some of the main scientific and engineering challenges in this domain. So, for example, deep understanding of the fluid flow around the wind turbine can be only achieved by some advanced techniques from computational fluid mechanics. And these techniques also should be capable of making full use of modern computer architectures. The computational challenges in our project are exacerbated by the need for analyzing and quantifying also fluid structure interaction. And in particular, this is the case for large wind turbines where the structure flexibility cannot be ignored. Another research question in the HPCW project is about estimating wind energy resource onshore in complex terrain and offshore where direct measurements of wind flow are not so easy to make. And we are addressing this particular challenge by high performance computing again, and this results in some high resolution models and some detailed simulations as well. And whenever we resolve the challenges and answer the research questions, we are also trying to strengthen up the collaboration between the teams in Brazil and Europe. So if we look at the schedule for the workshop, you probably have noticed that in the first day, day one of the workshop, our focus is more towards modeling and simulation of complex fluid flow and also fluid structure interaction for wind energy. And today's schedule consists of one guest speech and 5 presentations by HPCWE consortium members. So before we start the presentations, I would like also to mention something about the organization. So essentially, we have asked all the speakers to allow between 5 and 10 minutes for questions and answers, and we want to keep this at the end of each presentation. And this again for the purposes of recording this session, it's easier if we keep the questions at the end of each presentation. And we will have also a couple of breaks during the afternoon or the morning for some of you. And I will try to stick to the time as much as I can because we expect also people to join in and to leave at some points also the presentation. So we try to be strict in terms of the time schedule. So essentially, if you don't have any questions to us, to the organizers, you can write the questions also in the chat. We are following the chat as well on WebEx. If you don't have a microphone, please do ask any questions if you have before we start for the organization. And I'll ask also participants to mute their microphones and not to share their video when other people speak. But when you have a question, please unmute and also show your face if this is okay with you. Okay, thank you. I don't see any questions coming from the chat. And we are slightly ahead of the schedule as well. So before I introduce the first speaker, I will give him the opportunity to settle in with his presentation then, and then I will introduce him. I already saw Dr. Silvain Laizet online, so Dr. Laizet, please set up your presentation and I will introduce you in a few minutes' time. Thank you.
Thank you very much for the introduction, and thank you very much for inviting me to this workshop. I'm very happy to present some of our latest results. So some of them are not even published, and I've noted that I will try to stick to the timetable and leave some time for question. But so first of all, I would like to thank my collaborators, Georgios Deskos from NREL, Amy Hodgkins, who is a PhD student currently working with me, and Nikos Bempedris, who is a postdoc also working with me in the Department of Aeronautics. So the results that I'm going to present today were produced by those three collaborators. So I would like to thank them deeply, and I'm very honored to present their results on their behalf. So this is the outline of my presentation. I will have a small introduction. I mean, you are obviously all familiar with wind farms, so it's going to be very short. Then I will briefly introduce the wind flows solver that we are using for the simulation. And then I will focus on two aspects, on shear and thermal stratification, and how they are affecting the near-field wake development of wind turbine wakes. And we will be also looking at turbulence entrainment. So now the turbulence entrainment will be looking at the farm level, and while the shear thermal stratification is looking at wake level. And then I will conclude this talk with some conclusion. So you are all well aware that wind turbines are bigger and bigger. They are larger and larger. They generate more and more power, and this is obviously coming at a price. And in particular, I would like to focus your attention to this schematic. So they are extracted from a recent publication, and you can have all the information here. They are not from me, but the main conclusion here, and the key message I want to convey here is that the dynamic of wind turbine wakes is very complex. There is a lot of mechanism. There is some mixing. There is some breakdown of turbulence. There are various instabilities at stake. Due to the large size of the wind farm, we need to take into account atmospheric boundary layers. So we need to take into account shear effect. We need to take into account thermal stratification that might happen. We want to better understand the atmospheric turbulence mixing that is happening at the interface of the wake. We want to better understand the tip vortex spiral dynamics. We want to better understand the various instabilities that are happening. We want to understand when the wake is going to transition to turbulence. All these features have an effect on the power output of wind farm. So today in this presentation, I will be looking at three aspects of wind farms and wind wake. We will be looking at the effect of shear, the effect of thermal stratification at the wake level, and we will be looking at the atmospheric turbulence mixing or turbulence entrainment, and see how this can affect the power output of a large-scale wind farm. So all the results that I'm going to present today have been performed with our open source wind farm simulator called XCompact3D. And XCompact3D is a framework of high-order finite difference flow solvers. And part of the XCompact3D framework, we have a wind farm simulator called Wings3D. And as Flavio said in the introduction, if you're interested in using this XCompact3D framework, please register to the tutorials on Wednesday, and Flavio will be doing a demonstration on how to use XCompact3D. We have some ready-to-run simulation, I will say, so it's usually fairly straightforward to use this wind farm simulator. In terms of equations, we are solving, I'm not going to spend too much time on this, we are solving the Navier-Stokes equation. And the originality, I would say, of XCompact3D is that we are using a Cartesian mesh and high-order finite difference schemes. And just here, give you an idea of how high-order finite difference schemes look like. The key feature here is that they are implicit in space, which means that if you want to compute the derivative at the node here, you need to know the derivative at the node I-1 and I+1. Okay, so the idea here is that you are trying to mimic a spectral methods by allowing the schemes to capture a wide range of turbulent scale. And this is just an example illustrating the difference between low-order methods and high-order methods. So this is here, this is the wave number. So here at 0, you have large-scale features. At 1, you have small-scale features. And here you have the modified wave number, and the modified wave number will give you an idea of how much scales numerical schemes can capture. The black line here corresponds to when the modified wave number is equal to the wave number, which corresponds to spectral methods. So you get the exact derivative. So on the left-hand side, this is for the first order derivative. On the right-hand side, this is for the second order derivative. If you look at conventional second order schemes, they are able to only capture at a given resolution. They are only able to capture the large scale of the flow. And then they are missing all this feature here. So they are not able to capture the small scale of the flow. Once again, if you want your low order methods to capture more turbulence feature, you will have to dramatically increase the resolution. On the other side, you can see that the compact or implicit 6th order schemes that we are using here are able to capture a wide range of turbulence scale, while they are only missing the smallest scale of the flow. And this is the same for the second derivative. The point I want to make here, and this is something that is now widely accepted in the community, is that high order methods are highly desirable to study turbulent flow, because at a given resolution or with a given number of degree of freedoms, then you can capture more scale. So they are highly interesting with that respect. The second important aspect of XCompact3D is that it is based on a 2D domain decomposition, which means that we can efficiently use supercomputers based on CPU architecture. We are currently working on a GPU-friendly version of this XCompact3D solver, but at the moment, we are only using CPUs. All the communications, the global communication are based on MPI all-to-all. We are doing about 70 global transposition per time step, which means the cost of communication is between 30 and 80%. Just to give you a brief introduction to XCompact3D. So you start with a domain decomposition in X pencil. You do all your calculation in the X direction, and then you switch to the Y pencil decomposition, and you do all your calculation in the Y direction, and then you do the same thing in the Z direction, and you can switch from one domain decomposition to another. And this way, there is no overlap between the calculation and the communication, and which means that the parallel efficiency is really good. We did some benchmarking with up to 1 million core, and you can see that if the number of mesh nodes per CPU core is large enough, typically above 50,000, then the scalability will be excellent. If your number of mesh nodes per core is too small, then of course you will produce too many communication, and the scalability will not be that great. But once again, if you have the right balance of mesh node and core, then the scalability will be excellent up to 1 million core. Regarding the let me try to put a movie while you are waiting. Regarding simulating wind farms, we are using customized actuator line or actuator disk method. So I'm not going to spend any time on this. You are all very familiar with those techniques. And here you can see a small movie to highlight the importance of wake-to-wake interaction, where you have two wind turbines aligned. You can see that there's a dramatic power reduction. So here there's a first turbine, here there's a second one. And when you shift the first turbine with respect to the second one, you can see that the power output is actually not too affected. So this is just to highlight that XCompact 3D is designed for high fidelity simulation of wind farms, and we can really try to focus on wake-to-wake interaction, and this is what I'm going to present in the following. So the first part of the results is going to focus on idealized setup to look at the influence of shear and thermal stratification. So this is the computational domain. We are only simulating the blades. We are not simulating the tower and the nacelle. We are not simulating a proper atmospheric boundary layer, but we are going to try to take into account shear and thermal stratification. So the computational domain is 10R by 10R by 10R, R being the radius of the blades. We are looking at lab scale turbines. The radius is 10.24 meters. We are using 513 cube mesh nodes. The Reynolds number is 30,000, and the dx is equal to dy z equals 0.02 meters. And we are just going to impose 3 different shear intensity in the inflow boundary condition with 0, 10, and 20%. So those values are, of course, representative of what you will get for modern large-scale wind farm in real-life application. Okay, these are values that are typically encountered by large-scale turbines. We are also looking at 3 different thermal stratification: 0%, 1%, 2%, and once again, those values, they may appear small. They are small, but this is the temperature difference that you will experience in a modern wind farm, no more than 2% typically. In order to trigger turbulence, we need to impose some perturbation. And basically, if you do not impose any perturbation, because the flow solver is so accurate and is conserving energy, then if you start with a uniform velocity profile, then the wake will remain laminar. So it is important to add some perturbation, and we are adding the perturbation at the location of the turbines, and we have 3 perturbations characterized by their wave number, 3.5 and 9.5, and typically what it says, the 3.5 means that you are imposing a perturbation with 3 lobes like this, and 9.5 with 9 lobes. The idea of this perturbation is that you are going to trigger the mutual intense instability that is responsible for the pairing of the tip vortices. I will show you more detail here. So this is, so we did the 3 by 3 by 3. We did the 27 simulation. I'm not going to present results from the 27 simulation. I'm just going to present you with a selection of results. So what we can see here, we can see the vorticity fields. On the left-hand side, you have no shear. In the middle, you have 10% shear. And on the right-hand side, you have 20% shear. You can clearly see the effect of the shear, of course. It's impacting the tip vortices, and you can see they are slightly shifted. And the distance between 2 vortices at the top is much bigger than at the bottom. This is mainly the shear effect. And from top to bottom, you have 0%. You have 0 perturbation at the top. In the middle, you have perturbation 3.5, and at the bottom, perturbation 9.5. And you can see that well, shear is impacting dramatically the breakdown to turbulence, but also the wave number of the perturbation has also a dramatic effect. I was talking to you about, let me switch to laser pointer. What I was talking about is those perturbation or out of phase perturbation that are triggering this the pairing of vortices between the tip vortices. They are supposed to be parallel in the laminar region, but then they are starting to be less parallel. They are starting to interact together. This is the breakdown of turbulence, and eventually, we are only focusing on the near field wave, but you can see that the wake is eventually becoming fully turbulent. You can see that it's becoming turbulent when there's shear. It's becoming turbulent at the bottom. Okay, but if you count the number of vortices here at the top and the number of vortices here at the bottom, they are the same. It's just the distance between them is a bit larger. In our setup, the root vortex is not important. We have been trying to minimize the root vortex so that it does not affect our study. So the first thing we're interested in, we want to see if thermal stratification is going to have an effect. We know shear is certainly going to have an effect on the breakdown to turbulence. We know that the type of perturbation and the wave number is going to have an effect as well, and this is what I'm going to discuss here. So if we start by discussing the effect of shear and the effect of the perturbation. So here we are focusing on the perturbation 3.5 and 9.5. So we are discarding the zero perturbation. We can see that 3.5 means that we are going to have a pairing of vortices at 3 different locations. So you can see the imprint of the perturbation here. So at the start, you can see that. So here, this is the same as this plot here, but we are plotting the vortices in a plane. Okay, so this is a projection on the plane, so we can better see what's going on. So you can see that they start parallel, and then eventually in the transition region, they are going to start being less parallel, and then they are going to start merging together. When we go from 3.5 to 9.5, instead of 3, we are going to have 9, 1, 2, 3, 4, 5, 6, 7, 8, and 9 different locations for the pairing. And if we look at shear, we can see that shear is going to promote this mutual inductance instability. The tip vortices are going to interact together sooner. And this is also the case at 20% shear, but here it's you can see that there is one dominant pairing area, which is in the middle of the 180 degrees in the middle of the plot here. Okay. When you switch to 9.5 perturbation, you can see that you have a similar effect. You have more pairing. Okay, but at the end of the day, you get a fully turbulent wake in the middle of the figure, and more or less at the same location, 2 radius downstream of the blades. Now, if we're interested in the thermal stratification, we need to look at the different colors. So blue is 0% thermal stratification, green is 1%, and red is 2%. And we can see that pretty much for the breakdown of turbulence, thermal stratification has only a very, very limited effect. You can barely see the blue and green color on those figures. So one of the first key results here is that when we are looking at the breakdown to turbulence, thermal stratification only has a very, very limited effect, while the shear is promoting the breakdown to turbulence. So this is the first key message here. We can also look at the size and the shape of the wake. So here we are looking at the 27 simulation. We are looking at the shape of the wake after 1, 2, and 3 radius. So left, middle, and right, and top to bottom. Top is with 0 perturbation, 3.5 perturbation, and 9.5 perturbation at the bottom. The key figure here is that when you have shear and thermal stratification, the wake is slightly shifted downstream. It's a little bit bigger on the size, and it's mainly bigger at the bottom of the computational domain. At the top of the computation domain, there's no much changes. And if we look at the area, and we are interested in the area difference with respect to the uniform case where there's no shear and no thermal stratification, you can see differences up to 16%. So when you combine shear and thermal stratification, there is a significant effect on the wake dimension. If you only look at thermal stratification, right, the difference are very small. So you can see here we're talking of difference of 1, 2, maybe 3%. So thermal stratification alone is not doing much. But it's very interesting to see that when you combine shear and thermal stratification, you have a dramatic effect. And we can look at those numbers here. When you only have 10% shear, you can see that the difference with the uniform case is at 3R downstream is only less than 1%. Now, when you have 10% shear and 1% thermal stratification, we go to 2%, and then we go to 4%. Now, if we look at 20% shear, we go from 3 to 10, and for the case of 9.5, we go from 9 to 16%. So there is an effect of thermal stratification, not on the breakdown to turbulence, but there is an effect on the size and the dimension of the wake. Okay, so thermal stratification seems to only be affecting the wake development when it is combined with shear, and the main effects can be observed on the bottom half of the wake. You can see that the wake is a bit fatter on the side and on the bottom, where at the top there is very little difference. We also looked at POD. I need to be conscious with time. I can see that I'm going to run out of time. So that we are looking at POD modes as well, and we can see that basically the flow is mainly driven by two pairs of POD modes. So these are the dark blue here, and so this is the first pair of mode. This is the second pair of mode, and you can see that the first two pair of modes, they contain more than 80% of energy. You can see that when you are adding shear and thermal stratification, there is very little differences on this. The main differences you will see is that 20% shear plus 1% thermal stratification, which is actually when you will observe an earlier breakdown of turbulence. So basically, because the wake is becoming turbulent sooner, then the energy distribution among the wakes is wider. So the energy content of the first 10 pair of mode is a little bit smaller, but there is nothing much we can see here. What is going to be more interesting is to do some POD, but we are going to do some POD where the wake is laminar, where the wake is transitioning to turbulence, and when the wake is fully turbulent. Okay, so this is how we are defining the linear transition and turbulent regions. Okay, transition is when the tip vortices start to interact with each other. Okay, so we can split that, and you can see this is a very interesting plot. So we are dealing on the left-hand side the linear region, in the middle of the transition, and at the end the turbulent region. You can see that the black circle correspond to the helical spiral modes. So these are the modes related to the tip vortices. The square correspond to the mutual inductant instability. This is triggered by the artificial perturbations that we are imposing. And you can see that in the linear the region, the dominant modes are the helical spiral ones, which mean that the flow and the wake is driven by these helical vortices. The perturbation is not affecting the flow. And when you switch to the transition, the dominant mode is becoming the mutual inductance instability. So that's the one that is going to trigger the breakdown to turbulence. You can see that both pair of modes, so the helical spiral ones and the mutual inductance one, they more or less have the same level of energy. So they are competing with each other. One is trying to maintain the laminarity of the wake. The other one is trying to transition to turbulence. And of course, when the flow is becoming turbulence, the main dominant mechanism driving the flow is the mutual inductance instability mode. So by doing this, and sorry, I cannot spend too much time on this, but we are able to fully understand the different mechanism, and more importantly, we are going to be able to see how the wake, for example, the shear is affecting the flow. So you can see that the shear is reducing the effect of the helical spiral modes, which mean that the shear, sorry, will contribute to the breakdown of turbulence. And we can see that, well, it's very hard to see very quickly, but the thermal stratification is not really affecting the energy content of those modes. It's mainly the shear that is going to increase the influence of the mutual inductance instability and reduce the influence of the helical spiral instability. Right, I'm going to switch this slide because I don't have too much time, but basically we also look at fluxes. So you take a given radius and you look at the fluxes, and this is a nice way of understanding how shear and thermal stratification can affect the fluxes, and the fluxes are directly connected to turbulence. The more vortices you have, the more fluxes you are going to have between the ambient fluid and the wakes. Sadly, I want to be able to spend some time on the second part of the talk, so I'm going to skip this one. So I think I have about 10 minutes max to talk about turbulent entrainment. So this time we are going to look at a farm level problem, and we are going to look at turbulent entrainment. So there is a well-known picture of modern wind farms from the annual review by Stevens and Meneveau, and you can see that this is what we are going to understand. You have the incoming atmospheric boundary layer with or without thermal stratification. Then you have an internal boundary layer, but then also you have turbulent entrainment of wind kinetic energy happening at the boundary between the wind turbine wake and this internal boundary layer. So in order to do that, instead of doing a precursor simulation and then the simulation of the wind farm, we are combining the two together. Okay, so these are the parameters of the simulations here. So now we are looking at large-scale wind farm in real life. We are going to look at 3 different configurations. So fully aligned configuration, we are doing 26 rows, fully staggered configuration, and half staggered configuration. The spacing, the streamwise spacing is 7.85 diameter. The diameter is 100 meters. The spacing span-wise is 5 diameter. It means that, don't be afraid, but the streamwise distance is 7 diameter. So it's roughly 785 meters. So when you look at those figures, the axis is in meters, but don't be surprised by the distance and the dimension. We are looking at a very large scale wind farm. In the previous study, we were using the actuator line model. In this study, we are using the actuator disk model. So this is just an idea of the 2 boundary layers. You have the internal boundary layer here. You have the 26 rows here, and this is the atmospheric boundary layer. This is characterized by 0.99, so this the delta 99 criteria you can see here. You can see that when you switch from fully staggered, fully aligned, half staggered, there's not much difference here in terms of where the boundary layers are, where are the interface between the wake and the boundary layers. This is the mean flow velocity you have an incoming free stream velocity of 11 meters per second, and this is the kinetic energy. This is average in the span-wise direction, of course. What we are interested in this entrainment parameter, and there was a study by Lozzato and Caulfield in 2018, and they work out a formula for the power density of large-scale wind farm. And in this formula, there's a lot of parameters, but the one that we are interested in this entrainment parameter, and also this CM coefficient, which is in that study was assumed to be proportional to e to the 4. Okay, and this entrainment parameter is often assumed to be constant, assumed to be about like 0.1. Okay, and you can see that this entrainment coefficient is going to affect the power density of the wind farm. So it's very important to study this entrainment coefficient. So if we look at the value of this entrainment coefficient, the definition is given here on this slide. You can see that there are some small differences, especially in the first few rows. So first of all, we can say that for finite wind farm, finite size wind farm, this entrainment coefficient is definitely not constant as we are expecting. We can see that there is an effect of the arrangement of the farm. So this is what you will get. This is the entrainment interface for the fully aligned, fully staggered, and half staggered. And you can see that when you switch from one to another, the power output, the entrainment coefficient is going to be affected by, we knew that, but we have a confirmation now, is going to be affected by the spatial arrangement of the turbine. And more importantly, we know that now this effect up to 15 rows is going to be quite important. After 15 rows, you will argue that the epsilon, the E coefficient, is more or less the same. Okay, but it's still not constant. Okay, this is another important result. It's still not constant. It's slowly going down to a constant, which is, by the way, much smaller than 0.1, but it's still not yet constant. So if we look at the power output for the generic wind farm that we are investigating, we can see that the power output, which is directly proportional to the entrainment coefficient, you can see that it's quite important. And you can see that when this entrainment coefficient is more important, then you can see that the power output is less important. So this is ongoing work, of course, and we are still trying to make sense of all these data, but we are very much looking at entrainment and momentum transfer, and we are trying to understand how this turbulent entrainment is behaving when you change the spatial arrangement of the turbine, and also we need to look at when you play with the turbulence intensity of the incoming atmospheric boundary layer, and so on and so on. So I think I'm going to stop here if I want to be on time. So I would like to thank you very much for your attention. I would like to thank again Nikos, Amy, and Yorgos, who have been producing those results. Unfortunately, I cannot send you a link to publication. This is ongoing work. We are preparing the manuscript, so please stay tuned for hopefully some publication very soon. So thank you very much for your attention, and I'm open to questions.